Hi, I'm Ibrahim Kilinc, and today I'll be presenting our work titled as Position-Aided Beam Management for Multi-Panel Dynamic Metasurface Antennas. And this is a joint work with my colleague Nitish Deshpande and our advisor Professor Robert Heath. And this work was presented at Asilomar Conference on Signals, Systems and Computers 2024. Before going into the details of our core contributions, let's start with introduction. In this work, we consider multi-panel dynamic metasurface antennas, which are known as DMAs. And the DMAs are the antennas that has a waveguide in which the signal propagates through the feed to the antenna end. And each DMA waveguide has multiple radiating elements that are tunable, and each radiating slot radiates electromagnetic waves. And the tunable radiating slots are enabled through circuitry elements such as reactive diodes in order to enable beamforming in the antenna. And thanks to the reconfigurability, DMAs can replace some circuitry components such as phase shifters in the conventional phase arrays. And in turn, DMAs provide energy efficiency beamforming solutions. Here, however, the DMA beamforming weights follow a constraint which is called as Lorentzian constraint. And the constraint couples DMA beamforming amplitude, weight amplitude, together with the phase. So it complicates the beamforming solution as well as limits the angular beamforming coverage. In this work, we consider a DMA panel that is shown in the figure, and this kind of multi-panel increases the angular coverage. An example application in vehicular communication systems is given. Such antenna array structure with multi-panels can be placed into the car's shark fin to enable beamforming and energy efficient communication for vehicular systems. So shortly, DMAs with multi-panel antennas enable low power beamforming as well as increases the angular coverage. Let's talk about the importance of position information in relation to the beam configuration. And beams are special filters in 3D space where they amplify the signal from a particular direction, and they reject the filter signals from particular directions. So for a given environment as shown in this figure, there are two vehicles and a base station, and there are many static objects such as buildings, lampposts, and the mobile objects consist of are vehicles or pedestrians or other mobiles you can think of. And the channel is dynamic, but some part of the channel represented by static paths, and some of them are through dynamic paths. And for a given location and multiple paths, based on the works in localization literature, the user can be localized. And so in turn, the position information can be useful to infer some information about multipath information, and in turn for beam directions. So in the work given below, a technique called inverse multipath fingerprint is explained. So the position characterizes the multipath and beam directions in dynamic environments and can be used for the beam and panel configuration for multi-panel DMA antennas. Prior work in the literature has a lot of work in position-aided beam selection. Here, we identify the limitations of prior work and explain what our contributions. The common approach in prior work is to have a black box model where the position information is inputted, and at the output, a wireless specific information such as received signal power is predicted to select k subset of beams, where there are base station beams and the UE beams, and these are called beam pairs. And a beam pair subset is selection for dynamic environments because for a given position, there might be another vehicle or another obstacle where the beam can change. So selecting a subset is necessary for such dynamic environments. And the common approach in the prior work has limitations. such as fixed codebooks, the model is specifically trained for fixed antenna orientation, and the models assume mostly single panel, fixed antenna element, and fixed panel size. So in reality, the devices, UE devices, has different vendors and different antenna geometry, and even the position of the antenna is different. So the method is not flexible for different codebooks without retraining. There can be multiple models, but training model for each antenna configuration, each codebook, is not scalable. So orientation-aware beam selection, antenna multi-panel operation, antenna elements aware beam selection, and beam selection for variable panel sizes is missing in the prior work. So it's underexplored. In our work, we propose a UE panel and beam selection method for dynamic metasurface antennas, and the proposed method is agnostic to the codebook and antenna geometry. So the main idea is to decouple wireless propagation characteristics from antenna configuration. For a given location, at the exact same position and the environment, changing the antenna configuration doesn't change the wireless propagation characteristics. So the same propagation can be used to infer the best possible antenna configuration, panel, and the beam. So our method is two-stage, where the first stage is to, given the location information, the model predicts an angular power grid, and which we claim to be antenna heterogeneity agnostic. And the second stage takes angular power grid as an input, and the codebook for the antennas, and the antenna type, panel, and panel size, where these parameters are fed as an analytical input. So the K subset is selected. So the proposed solution specifically focuses on the UE panel and beam selection, and performs for varying types of codebooks, antennas, even antenna type, and panel orientation, if the polarization angle of the antenna element doesn't change. Let's formally talk about the system model and proposed solution in detail. The system model consists of a base station. The base station consists of a uniform planar array, and it's connected to an RF chain with fully connected phase shifters. And the beamforming happens, base station is an analog beamforming. And the UE side has three DMA panels, where one DMA panel connected to RF chain at a time. So the panel switch occurs through a panel switching circuitry. And on the left below, the Lorentzian constraints, where each DMA slot should follow, is given. And the downlink receives signal for the P panel, and for a given DMA combining and base station beamforming is given for the K subcarrier. In this slide, we explain DMA channel model and 3D beamforming weights for DMA elements. And on the left, P DMA panel is shown, where on the vertical axis, NRZ waveguides are, and then in the horizontal axis, there are NRY radiating slots, where each DMA waveguide has. And the wireless propagation channel is modeled through dipole approximation of DMA radiating slots. And in addition to the wireless propagation channel, the electromagnetic wave travels through waveguide in electric current, and it creates intrinsic waveguide channel. The model is given in the below. So we obtain the DMA channel for the P panel by applying the intrinsic waveguide channel to the propagation channel with the dipole approximation of radiating slots. And the expression is given on the slide. And the beamforming weights for particular azimuth angle phi and elevation angle theta and particular frequency, operation frequency, is given in the below. For more details about DMA channel model and 3D beamforming, of DMA elements, you can check out the paper below. So far, we explained the system model, the DMA channel model, and the beamforming weights for particular azimuth and elevation angle, where the codebooks, DMA codebooks are obtained from the sampled azimuth and elevation angles. And the beam and panel selection problem is stated as follows. In this work, we make some assumptions. However, our proposed solution is not tied to these assumptions strictly. And UE knows its location and orientation, which can be done through some sensors such as GPS and IMU sensors. And nowadays, most of the devices are equipped with those sensors. And we assume single panel transmission, and we assume that the base station beam is known. So this assumption is made in order to focus on the UE side of the problem and the beam and panel configuration at the UE, not the base station. So our method is not strictly tied to these assumptions. And we assume there is a collected power measurements for beam and panels across all panels. And this dataset can be collected through drive tests or RSRP feedback in 5G, which is a standard feedback. And we assume there is an offline learning at the base station that trains our method. However, we do not specify, and that part of the work is left as a future work. And the main problem is to select a subset of beams with panels to maximize the receive power. So we identify two sub-problems in this beam selection problem. The first problem is to obtain angular powers from the receive power measurements. And the angular powers are agnostic to the antenna configuration and codebooks. So the second stage is for a given angular power and the antenna heterogeneity, how to obtain the receive powers back from the angular power. And this part should be analytical, so that for given orientation, for given codebook, and for given angular power for an environment, we can obtain the receive powers directly. And let's talk about the proposed solution for problem 1 and 2, which is explained in the previous slide. And the main idea is to exploit the beam pattern for each beam combined with power measurements. On the left side, you see a beam pattern for default antenna orientation, where the orientation is governed by alpha, beta, and gamma parameters, which is the rotation around Z, Y, and X axis respectively. And the beam pattern for P panel and end beam is given here. So when the orientation changes, the beam pattern is also rotating with respect to the orientation. So for given power, for P panel and end beam, we can represent that receive power as a dot product of X, vectorization of X, and vectorization of A and P. And the X is a non-zero power matrix that we explained in the previous slide, and A, P, N, which we denote as a beam mask. And the beam masks are analytical, which can be calculated for any orientation from array mask. And the optimization problem is to solve X for given receive power measurements across all measurements. And here we briefly explain how to obtain beam mask mentioned in the previous slide. The beam gains shown in here for different beams from the UE codebook are shown within elevation and azimuth angles, where elevation angles are from 0 to pi and azimuth angles from minus pi half to the pi half. And beam gains are calculated from the array factor. And for given antenna orientation, alpha, beta, and gamma, using the composite rotation matrix, the beam gains are rotated. And then they're quantized with respect to the delta phi and delta t. The quantization helps in order to reduce the computation complexity and to obtain the receive power as a just simple dot product. And the constraint convex optimization problem solved in previous slide is solved via CVX to find the angular power matrix for X, which is antenna configuration agnostic. So the overall offline training and beam selection procedure is as follows. For given location, there is a receive power measurements that are tied to beams, antenna sizes, antenna elements, orientations. So using the optimization method, the global grids are obtained, and they form a labeled dataset where L is the input and the global angular power grid is the feature vector. And together with multi-output regression, the following model angular power predictor is trained. For a given location, the network predicts x hat, which is the angular power matrix. So once the angular power matrix is predicted for a given antenna heterogeneity and orientation, codebook, and so on, they are represented as vectorization of APN, and the receive power is obtained through the equation 4 with just simple dot product. Let's dive into the simulation results. In our simulations, we consider vehicular communication scenario. However, our proposed solution is not limited to vehicular communications. It can be applied to cellular communications as well. So we consider mobile vehicles where the cars are UEs and the buses are reflectors or blockers. And the traffic mobility is generated through Sumo in conjunction with Siona ray tracing to generate spatial consistent channels. And the simulation parameters are given in the table, where the base station has 8x8 UPA with DFT codebooks and fixed antenna orientation. And the DMAs and UPAs are used at the UE at the same time to compare our method in varying antenna types and varying antenna sizes for 3x3, 4x4, and 5x5 antenna arrays. And the other parameters are given there. In the simulations, we use the baseline from the paper cited below. And the baseline is simply follows. There is a black box model that takes the location and orientation per panel and predicts the receive powers for each beam for that panel. And for our method, we use XGBoost regressor to predict angular power grid over different locations. And the performance metrics are given as power ratio and misalignment probability. And the expressions are given in the slides. And the power ratio in dB highlights the receive power loss to the best achievable beam panel in the codebook. And the misalignment probability is the probability of not selecting best panel and beam. And this plot in red curves shows the power loss from the best beam and panel. And as you can see, for different DMA panels, different sizes, and different UPA panels as well, where the method is trained only for 5x5 DMA. Our method is able to achieve better power loss performance than the baseline, and it generalizes well across different antenna configurations and sizes. And in terms of misalignment probability, it's achieving up to 10% of selecting total beams over all panels. It achieves better than the baseline, and the misalignment probability decreases as the percentage of total beams over all panels are increasing. So even though misalignment probability is harder to achieve, the proposed method can generalize well over different codebooks, antenna sizes, and types. In this plot, we show user-for-user generalization performance through empirical CDF. So the proposed method is again trained on 5x5 DMA and tested on different antenna configurations, UPA, DMA, and different sizes. So overall, the possibility of 0 dB power loss for 98% of the test users in the urban street when tested on the same antenna configuration. And the possibility of 2.5 dB power loss at the worst case for more than 80% of the test users is achieved, while generalizing over codebooks, antenna sizes, and types. And the baseline is also trained and tested on 5x5 DMA in this plot. To conclude, the proposed beam panel selection approach achieves generalization over different antenna sizes, codebooks, and even antenna type with the same polarization. The beam and panel selection approach seems promising in realizing multi-panel DMAs for low-power applications. And in the future work, we will explore the extension to polarization mismatch with 3D orientation change of DMAs for handsets, DMA codebook optimization to increase generalizability. Thanks for listening. If you have any questions or follow up with my work, you can leave a comment below or send me a message through LinkedIn where the QR code is given below, and email me at ikilinc@ucsd.edu. Thanks for listening and have a good day.